Last time we were together, I had you make a Christmas box, but the real purpose of the problem was to see if we could optimize volume, of an open top box. Of course, you tried to figure out what cuts you would make in the corner, and then we realized that we could actually create an equation and really optimize the equation. That is, try to find the maximum volume. Well, when we talk about optimization problems for lesson 4.4, it's a fact that optimal values will always occur at a maximum or minimum. Now, what you want to remember, even though it seems like it was last year, well, it was, but what you want to remember is that we spent a lot of time finding maximums and minimums, of course, using the derivative equal to 0. And when the derivative is equal to 0, you're at a place where the slope very well might be changing from positive to negative or negative to positive. I'm talking about a number line, and when you create that number line, then you find your max and mins. What's going to happen now is we're just going to be doing this for equations that actually represent something. Most of the equations are going to represent something geometrical, but we also will do some economic equations. So we're trying to basically create big or small shapes. We're trying to get optimal values, and we're going to do this again with the derivative equaling 0. That's the easy part. What you're going to learn is that the harder part now is that we actually have to come up with these equations. Now, to come up with these equations, it turns out that the way that the problems are set up is that we're going to follow a process. The process is that we're going to first create a primary equation. Now, the primary equation is going to be the equation that we're trying to optimize. It's going to be the quantity. It's going to be the word. It's going to be the geometry idea that we're trying to optimize. So we'll make that the primary equation. But it turns out that we're going to most likely also need a secondary equation for most of these problems. Now, the secondary equation isn't just kind of extra needless information, but you're going to find out be a formula, an equation that we have to create most often so that we can substitute it into the primary equation. So you'll see, we really didn't have a secondary equation for our Christmas box. We just had a primary equation, which was the volume. But the idea of the sketch kind of became like the secondary equation because it helped us to navigate the letter X. All right, so we've done a problem, but let's kind of do, so to speak, our very first problem where we're going to try to use this process of a primary and secondary equation. Okay, so we're going to try to come up with the smallest perimeter of a rectangle, so just a good old two-dimensional rectangle that has an area of 36. Now, it actually turns out this is a pretty easy problem. You could probably figure this out just with a little bit of common sense thinking, but I want to show you the process on an easier problem, and again, that's by design. So the first thing that we need to do is we need to come up with a primary equation. Now, the primary equation is always what you're trying to optimize. And so I hope that it's very clear in this problem that it's going to be the idea of perimeter. So literally, the primary equation is the perimeter of a rectangle. Well, we don't have to go searching in the farthest depths of the world to know that the perimeter of a rectangle is basically two lengths plus 2 widths. Why don't we make it 2L and 2W? I just always get concerned about the letter L. It kind of can look like the number 1 sometimes. But basically, it's the same perimeter equation from geometry. How about the secondary equation? The secondary equation. Wait, it seems like we have some other information here, and indeed we do. It has to do with area. But what we find out is that we know that of course, we know that the area formula is length times width, but what we find out is that we know that length times width has to equal 36. So you're going to learn that the secondary equation is kind of like you know a little bit more about it. In this case, we know what it equals. Okay, so we're going to actually use that number 36. Now remember, the idea here is to optimize this primary equation. That basically means we're going to do the derivative. But who's excited about doing the derivative of 2L plus 2W? Well, we've never learned how to do the derivative with two variables. And so that's what the secondary equation's for. You see, the secondary equation's actually going to be able to substitute in for one of these variables, basically creating a perimeter equation that we then can derive. So your secondary equation, you're going to solve it for your favorite variable. You want to solve it for L? You want to solve it for W? It doesn't matter. I'm going to make the decision to solve it for L, and of course that is then what we're going to substitute in here for L. So now we're ready to kind of, you might say, sort of rewrite the perimeter equation. I'm going to use like function notation P of W because I want you to see here that we're actually now creating an equation in terms of W. So I did the substitution. Now I have 236 over W plus 2W. Okay, and that equation, of course, can be simplified. You should always simplify, kind of do algebra most of the time. Do algebra before you do calculus. All right, so do you see what's going on here? We've got a perimeter equation that's now written in terms of a W, but of course that came from that idea of the area, that secondary equation being substituted in. So enough talk, we're ready to do the derivative. We're ready to actually do the calculus step. And so I'd like to say nothing new here, but I feel like it's been a little while since we did a derivative. Remember 72 over W? We spent a lot of time early in the year talking about how that is the same as a negative exponent. It's fine if you can do that in your head, but I just want to make sure you can see that I'm going to bring down a -1. I'm going to subtract from -1 and get -2. Of course, negative exponents are better suited for the denominator. So we did the derivative of the fraction, and we're going to do the derivative of 2W. I'm pretty sure that's just 2. And we got our derivative. So what are you waiting for? You want to set that thing equal to 0, right? Yeah, we want to set it equal to 0 because we're trying to find a critical point. Basically, we're trying to find a maximum or minimum, actually sort of give it away, but we're trying to find a minimum for this problem. We're trying to find the smallest perimeter. Okay, but let's solve this thing. It's equal to 0. What do we want to do? A little bit of algebra. I don't like negatives, so, do we realize that if you kind of clean this thing up, you're going to end up with basically -72 over W squared equaling -2. But we don't really need those negatives. We can just multiply both sides. Keep solving this. I think you're going to divide, you're going to multiply the W squared over to the other side and divide the 2 back over. Of course, when you divide the 2 back over, you get 36 equaling W squared. So 6, that is plus or minus 6, would equal W. Now, what does that mean? Well, that's supposed to signify that a positive or a -6 for a width. Well, now, wait a minute. For the width of a rectangle, it's not going to make any sense to even talk about the negative value. In fact, it's really not going to make any sense to even go anywhere past 0. So it's almost like 0 is kind of one of my endpoints, if you will. So I should be testing some numbers that are, between 0 and 6, and then, somewhere greater than 6. What kind of numbers do you want to check in here? You can check whatever you want. Do you remember where we're checking them? We're checking them in our derivative equation. So if I plug a 3 in there, we basically end up with 72 over 9. That is -72 over 9. So we get like -8 plus 2. Well, that's going to come out negative. And if I plug in 7, I'm actually going to end up with a decimal, but it's going to end up being a positive number. So what do we think? Remember 6? 6 was actually my critical point. Hopefully you can see now that because the graph goes down by the negative slope and then the graph goes back up, that we actually do end up with a minimum. We end up with a minimum at 6. Well, that's the way this was supposed to work. So 6 is kind of our magic measurement, but what you want to remember is that this problem was asking us for the smallest perimeter. So we have to do what with 6? That's right, we have to plug it back in. Now, where are we going to plug it back in? We're going to plug it back into the perimeter equation. The thing is that you have a decision to make. You can plug it back into our original perimeter equation, which means that we also have to find the length. We can talk about that. Or you could plug it back into your substituted perimeter equation. You know, your one where it was only in terms of W. So either is going to work. I want you to see that, if you just kind of follow the idea of plugging back in, then we can plug back into our perimeter equation. It had just W. It was the one that was written as 72 over W. Let's get the colors right here. 72 over W plus the 2W. And so when I plug W back in here, we basically end up with 12 plus 12, which is going to come out to be 24. 24 units or whatever this thing was measured in, but we want to realize that that is a perimeter measurement. Now, we could have also found the corresponding length, since we already knew that the area, which was equal to 36, is of course length times width. We certainly could have solved this thing for the length, and I'm sure you've already noticed that means the length is also 6. Because what we have here is we basically have a square. So a square is always going to have the minimum perimeter, sort of the smallest perimeter, but yet still have that area that we want of 36. So just to kind of add to my answer here, the perimeter is 36 when the width is 6. Of course, we figured it out a while ago, but when the length is also 6. What do you think? The idea of an optimization problem. Okay, primary equation, secondary equation. We're going to need to be able to go through this process when we do a problem that's a little bit harder, like something like the least amount of material needed to create a can, a cylinder that has a volume of 1,000 milliliters. Okay, so we're trying to use the least amount of material, that is the least amount of surface area. So wait a minute, we need a surface area equation for our primary equation. So anytime you go through this process, the first thing to do is to identify what it is you're trying to optimize. But then you're going to quickly realize that the next thing to do is to come up with an actual equation for that surface area. Well, if you think about a cylinder, it's like it's got 3 sides. The top and the bottom, those are circles. And I think we know the area of a circle. But what about the third side, the side that's in red in this diagram? If you unravel the cylinder, you can see that the shape we're creating from that third side, it's actually just a rectangle. And I think we also know the area of a rectangle, of course, length times width. The question is, what actually is the length and the width? So, of course, the area of each of our circles here, the area of a circle is pi r squared, and, we've got 2 of those. So as we start to build this surface area formula, kind of the little easier part is to say that we have 2 pi r squareds. But how about this red section? How about this rectangle that we created? Okay, we know that the area of a rectangle is length times width, but what is the length? What is this this distance here that, again, unrolled to be a length? That's right, that's the circumference. That's the circumference of a circle. Now remember, the circumference of a circle is 2 pi r, but that is also like the length of that rectangle course, the width of that rectangle is going to be this dimension. Here it's shown kind of vertically. Most people would call that like a height. So the length is 2 pi r, the width is h. And we end up with a formula for the surface area of that red section, 2 pi rh. Of course, we want to add that on to our surface area formula. That is our kind of our overall surface area formula. Now, the purpose of this lesson isn't to kind of recreate geometry formulas, but you do want to be able to come up with formulas that are going to work with the shape that you're talking about here. So, we did a little bit of thinking. We came up with the surface area formula for a can. Again, that's our primary equation because that's the one we're trying to optimize. Eventually, we're going to do the derivative of that lovely thing, but it's going to be more lovely. It's going to be more doable when we get the secondary equation kind of built into this. So do you see how there's always another piece of information, or maybe I should say when there's another piece of information, we're going to use that to help with an eventual substitution. So remember now, the volume of a can is like taking the bottom. Usually we kind of think of the bottom circle is pi r squared, and then multiplying that by the third dimension. And the third dimension would be the height. So we're not going to spend a lot of time creating that formula. I just wrote it for you. It's pi r squared h. But the key here is that we know that's equal to 1,000. Now, this secondary equation eventually is going to substitute into this primary equation. But I have a question for you. Would you rather substitute h's or would you rather substitute r's? Okay, there's not necessarily a wrong answer, but if you look, you've got multiple places where there's an r. That's going to be a little tricky to try to substitute it for both of those, but there's only one place where an h is shown, so the idea is that's going to be a lot simpler to substitute. And so we want to solve this equation for h. We want to solve for h, which means we're just going to divide both sides by pi r squared. Okay, now again, we're solving this for h because we're going to take 1,000 over pi r squared, and we're going to take that, we're going to substitute it in here for h. And of course, when we do that, we're going to end up with an equation that is in terms of just r. So let's make a surface area formula. We'll call it S of r for surface area in relationship to r. It's still going to be 2 pi r squared. Nothing needed change there. And it's still 2 pi r, but now we're going to multiply it by h. And of course, h is this 1,000 over pi r squared. You were nervous about all this fractions and stuff, but look, some things are going to start canceling out. These pi's are going to cancel. The r's are going to reduce. And so it's not too bad. I end up with a primary equation in terms of r as 2 pi r squared plus 2,000, right? Multiply those, get 2,000 over r. Now, remember, in a lesson like this, it's kind of easy to get a little lost and say, all right, yes, sir, that's the equation. But remember, that's the equation for the surface area of a can that has a volume of 1,000. And if we take the derivative of that equation, then we'll be able to find a critical point. A critical point, basically a critical radius. And that critical radius is going to help us to eventually get what we're looking for. What are we looking for? The least amount, the minimum amount of surface area. All right, let's do the derivative. Okay, bring your 2 down. Good old derivative of r squared. So we create a 4 pi r. This guy's a fraction, right? One more time, and I don't mind showing this. I think it's helpful. It's r to the negative 1. So when you bring down the negative 1, and when you subtract from it, you get negative 2, which is actually going to become a positive 2 when you flip it back. Okay, there's your derivative. Set it equal to 0. Okay, now you got to realize that this problem is, at this point, a little bit more algebra than it probably is calculus. Okay, you got to be sensitive to the fact that you've got r's in multiple places, and when that is the case, we want to try to get them in the same place. We're going to want to basically get this fraction, get rid of this fraction. We're going to kind of get rid of this r squared down here. I would probably move this over to the other side, and recognize that you're not going to have anything negative anymore. I'm going to go back to the color blue, but you see I can now multiply this r squared over here and basically create a 4 pi r cubed equaling 2,000. So that's not too bad. Finally, I have variable, just one variable in one place. Keep solving that thing for r, divide both sides by 4 pi. I'm not going to show that, but I'm going to do it. So you divide both sides by 4 pi and end up with a number around 159. Let's make that look a little better, 159. And then take the cube root. Yeah, take the cube root. Or you can raise both sides to the 1/3 power. I like to raise both sides to the 1/3 power because I don't have to go find special buttons on my calculator. Make sure you're comfortable with what's happening here. And that will end up giving us a radius of 5.42. Now, is that really like the minimum radius? Okay, well, these number lines, they still exist because you have to realize that we're still finding a critical point. It's just more like a critical radius. And so, I can plug some numbers in on this side and on this side. I'm going to be plugging them back into the derivative. I'm not going to actually show all that this time, but if you plug in if you plug in 2, you get a negative. If you plug in 6, you get a positive. So I do end up with a graph that goes down and then goes back up, which gives me sort of proof that 542 is a minimum. Now, what do I do with that? Okay, well, remember the question was, what's the minimum surface area? So one more time, I can take that number and I can plug it back in. Okay, but I want to make sure I'm plugging it back into my actual surface area formula. And that was that big crazy formula that had, once it was substituted, that had the 2 pi r squared. So, of course, that's where 542 can go, but also had the 2,000 that was over just r once I simplified it. And so I'd be plugging in that equation. The other thing that I could do, especially if the question asks me for the dimensions, is I could find the height. Keep in mind that the height we found from that secondary equation was described as 1,000 over pi r squared. Why am I doing this? I'm just saying that if the problem asks for the dimensions of the can, I would have the ability to actually go find this height, and then I could take my 542 and my 1084, and I could plug those back into the original formula. But either way, I end up with a surface area that comes out to be 553. Now remember, this 553 is really like the y value of the equation, but here it actually just represents something. I believe it would be centimeters cubed if you think about your chemistry. If the volume was in milliliters, then the two-dimensional measurements, the one-dimensional measurements would be in centimeters. But that's why this three-dimensional, hold on a second, I got my dimensions wrong. It's surface area, so it would be centimeters squared, but that would match with the milliliters for the volume. Are you ready to try a problem? Sometimes students are ready. They say, I'd like to kind of try to do one of these on my own. That's what this third one is intended for, although I probably need to do some setup for you, but I just want to give you a chance to jot this down and maybe be thinking about the primary and secondary equation. That's pretty important. All the problems start with primary equation. So what is it that you're trying to optimize? It says we're trying to find the area of the largest rectangle. Okay, that's supposed to kind of sort of trigger for you that we're trying to optimize area. I mean, that's what it says. Find the largest area. Okay, find the area of the largest rectangle if you kind of rephrase it. But basically, this problem, this primary equation, is nothing more than just the length times the width. Okay, yeah, a little bit like a problem that we saw earlier, but now the primary equation is this area. Okay, you don't know what this equals, okay? Be careful. You don't want to try to say this equals something. You're trying to come up with what's going to be the largest that this can equal. The thing is that this is an example of a problem that your secondary equation actually becomes more of a sketch. So I don't have an equation to write here, but I do have a sketch to create when we think about what it means to be a rectangle that's inscribed. Now, the square root of 4 minus x squared, okay, y equals the square root of 4 minus x squared. That'd be something that you would have to graph on your calculator, and you would see that you end up with a graph that it's actually a semicircle, okay, but you would use your calculator to graph that, and then continuing to think about what it means to be inscribed, we would be able to draw a rectangle. Hold on a second, let me get this fixed. Okay, so thinking about what it means to be inscribed, we would then realize inscribed just means that the rectangle is kind of inside of this semicircle. That is, its vertices, the vertices of the rectangle are denoted by the actual graph, the actual square root of 4 minus x squared. Okay, so this is an inscribed rectangle. Okay, what are we going to do with this now? Okay, again, I'm trying to give you a chance to do something here, but you have to realize that we've got a primary equation that's got two variables. It's got L and W. So that's not going to work. We need to try to turn this equation into basically just one variable. So why don't we talk about the length of this thing? The length being this distance down here. What do you think? What do you think about that distance? Okay, do I hear an x? Well, you're close. X is actually a measurement from the origin, so x would have to be just this distance. But that means, yes, that means we could call this 2x. How about the width? Okay, or basically the other dimension. How about the width? Do I hear a y? Well, yeah, you're right. It is a y value. It's basically a vertical dimension. But I don't want to use y as my other variable up here because I'm going to end up with two variables again. Does anybody know what y equals? Do you see it? That's right. Y equals the equation. So to write the square root of 4 minus x squared is actually to describe the other dimension of this, of this inscribed rectangle. Now, if I substitute this in, kind of like you do when you have a primary and secondary equation, so if I substitute this in, I'm going to end up with a primary equation that has one variable. That's right, it's just the letter x. So what does that mean? Well, that means it's time to do the derivative. The derivative of 2x times the square root of 4 minus x squared. The derivative of a product. That's right, we're going to have to use a product rule. Ready? Well, actually, you do it. You pause the video and you practice the product rule on this. You want to get started with the first and then the derivative of the second. All right, so how's that product rule going? First, derivative of the second. Did you think about the square root as a 1/2 power? Careful with my notation there. It's that the square root is the same as a 1/2 power. So bring the 1/2 down. Leave the inside alone. Oh, that sounds like the chain rule, right? Well, it is. You want to finish the derivative of the outside, so you get negative 1/2. Then you want to multiply by the derivative of the inside. Of course, the derivative of the inside is going to be a negative 2x. So that's first derivative of the second. Fun stuff. I still got the second derivative of the first. I'm going to write it backwards, though, because the derivative of the first is just 2. And the second is still the square root of 4 minus x squared. Now, the one thing about that square root of 4 minus x squared is at some point I'm going to have to decide if I'm going to write it with exponents or if I'm going to write stuff with square roots. But for now, I'll leave it as it is. And we're going to get ready to simplify this. Goodness, how am I going to simplify this? Well, one thing at a time. Okay, that's kind of a straightforward one. Those 2's can cross off. How about these x's? Yeah, I'm going to end up with an x squared, and I don't see that going anywhere. So it looks like we got a negative 2x squared, and then, yep, the negative exponent that's going to flip down to the denominator, make that exponent positive. How about the second part here? Nothing really simplifies, but as I was saying, let's change the square root notation into exponent notation. So what are we doing here? We're trying to simplify our derivative, well, so that we can ultimately set it equal to 0, right? It's an example of a common denominator. The only way that you're going to solve this derivative is if it's simplified into one fraction. So I need a common denominator. I'm going to multiply the top and bottom by the 4 minus x squared to the 1/2. Of course, these terms, both these circled terms are identical, so that gives me an opportunity to do Mr. Naylor's favorite exponent property. That's right, you're going to add them. You're going to add those exponents. You get an exponent of 1. Of course, that's convenient. So let's not do too much at once here, but I did make a common denominator, so I'm going to go ahead right now and sort of make one fraction. But remember when we added those exponents, got an exponent of 1. That means 4 minus x squared is to the first power. That's right, that means that I don't even need that exponent of 1, and that gives me freedom now to distribute this 2. We're getting close because I'm going to end up with the ability to combine some like terms. I get negative 2x squared twice, so that's going to be negative 4x squared. Of course, plus 8 with a little distributive property. There you have it. Okay, that's the derivative. Now, that was a lot of work, but we're not done yet. You got to set this thing equal to 0. That's right, you set the top equal to 0. And when you solve that, you end up with a critical x value. Now keep in mind that x value is actually part of a dimension of a rectangle. But basically, when you solve that, you end up with x squared equaling 2. And if x squared is going to equal 2, then x is going to equal the square root of 2. Now, technically, it's plus or minus, but yeah, we're not going to fool around with negative dimensions. But I still want to be technical and show that. What about the bottom? Wait, we're supposed to set that equal to 0? Well, yeah, you're supposed to find when the bottom is undefined. Now, the bottom's undefined when it's equal to 0, and the only way that's going to equal 0 is if the inside is equal to 0, and that's only going to happen with a regular 2. Okay, so I end up with some other critical numbers. Now, when it comes to a number line for this problem, we got a little bit more commotion, right? I've got the square root of 2, and then I've got a regular 2. Again, I'm going to leave out the negatives. We're not going to deal with negative dimensions, okay? But when you think about it, the number 0 would sort of be like an endpoint dimension. And so I can check any numbers I want in here and any number I want in here. Now, it gets a little tricky. A number that's in here might be a number like 1.75. Okay, but here, in this situation, in this section, in this interval, I end up with a positive slope. In this one, I end up with a negative slope. That means that my graph goes up and then goes back down. Is that good? Yes, it's good, because remember, we were trying to find the maximum. Okay, somebody says, is it always going to work out? Well, yeah, it's going to work out if you set up the problem correctly and solve it correctly. But it wouldn't make any sense to try to find a minimum rectangle inscribed in that space, because there is no minimum. I guess if you want to be technical, the minimum is going to end up being this endpoint here. But if you have a value of 2, you're going to find out that you don't have a rectangle, okay, because your entire dimension is taken up with just the width. And it's the same thing here. I mean, this is also a minimum, but if you have a dimension of 0, you also don't have a rectangle. So the problems are meant to work out. As long as you set them up correctly, we find out that we actually do get a maximum. But remember, you actually want to find the area. Wait, how do I find the area? That's right, you plug back into the area equation. Okay, not the derivative, but the actual area equation. The area equation was 2x's. Okay, so it's going to be 2 root 2's times the y value, basically the other dimension. So when I plug back root 2 back in here, I find out that I end up with the square root of 4 minus 2, which is actually just square root of 2. It's kind of interesting here that we end up with basically 2 times 2, a nice little even answer here of 4. Okay. Again, when we say that root 2 is the maximum, what we really mean is that it's the x value that gives you the maximum. You got to plug that x value back in. Oops, my notation was a little sloppy here. You want to plug that back in to your area equation, and you end up with a maximum area. We should probably label the answer here, maximum area of 4 units squared, when the x dimension is root 2, and turns out when the y dimension is root 2. Remember, this was our actual y dimension. Yeah, it's another square. In the case of this problem, I actually get a maximum area when I have a square shape. Those are optimization problems with more like geometry shapes. There's also optimization problems when it comes to economics. Now, we've talked before when we did economic application that I am not teaching you a business calculus type class, but we still want to expose you to some of these business applications. So we're going to kind of keep this simple. You can jot down these facts if you want. They're not meant to be something brand new to you. I mean, if you think about it, revenue is just like money that you make when you sell stuff. You know, if you're selling lemonade, okay, you know, people hand you $1 for every cup of lemonade. That's your revenue. The cost of your lemonade, okay, I mean, you had to buy the cups, you had to buy the lemonade mix, and then the profit. Okay, profit, that's actually different from your revenue because the profit, you have to subtract out your cost. And so that's actually, in the end, what you end up making sort of in the green, so to speak. So we have R of X, C of X, and P of X, basic economic words or symbols that we're going to use when we do some marginals. Now, we talked a little bit about marginals, again, when we did some application months ago. I don't expect you to be an expert, but basically a marginal is a derivative. But it's for economic derivatives. And what it basically represents is like what it would cost or what profit you would make or what revenue you would get for one more. If you sold just one more cup of lemonade, and that idea comes from a derivative. Now, main thing is I just want you to know that a marginal is a derivative, but the cool thing is that we can do some optimizing, like we can find like a maximum profit. You know, if you're selling lemonade, you want to try to make the most amount of money. You might think that that's by selling the most amount of lemonade, but technically it happens when the marginal revenue is equal to the marginal cost. Basically, you know, it could be that you sell so much of something that you end up starting to lose money. Okay, and obviously if you don't sell enough, then you're not making a max either. So the maximum profit, it's a simple calculus idea. It's just the marginal revenue, that is the derivative of the revenue, equaling the derivative of the cost. There's one more optimization that we like to have. It's minimum cost. Minimum cost. Okay, if I'm selling lemonade, I don't want to buy a whole bunch of extra cups that I don't use. Okay, so how does that work with calculus? Well, a minimum cost is going to happen when the average cost of your production is equal to the marginal cost. Now, I did throw a new word in there, average. So how do you get an average cost? Well, what you do is you take your total cost, C of X, and you divide it by the number of X's that you make. So again, C of X would be like your total cost of selling lemonade, and you divide it by how many lemonades you sold. That's the average, and we're just going to make that equal the marginal, which is the derivative. Now, don't worry about trying to memorize these formulas. You're not actually ever going to have to do that. We just want to be able to use the formulas. We want to be able to do an economic optimization problem. So here's some simple equations of some certain company. I mean, we can pretend that it's a lemonade stand if we want, but the revenue, it looks like it's 9x. That would seem to say that you're going to make $9, or maybe it's $9,000 for every X. So kind of a basic idea. Your revenue is 9X. Now the cost equation, X cubed minus 6X squared plus 15X, that's a polynomial. So, that thing's going to go up and down. I could imagine your costs would vary depending on how much X you produce. So what are we going to try to do here? We're going to try to find the production level that maximizes profit. That'd be certainly something you'd want, a maximum profit. And then we're going to try to get minimal costs. We're going to try to minimize our costs. Well, wait a minute. Wouldn't that be the same value? Wouldn't that be the same amount of X that gives you a highest profit but a lowest cost? Well, let's find out. Let's use the idea of marginals to basically solve this problem. So max profit. We had this little fact that is when the marginal revenue is equal to the marginal cost. Of course, basically the derivatives are equal. So let's do the derivative of the revenue. It's just going to be the derivative of 9x, so that's 9. And we'll do the derivative of our cost equation, a little bit more of the power rule being used, but basically we get a nice little 3x squared minus 12x plus 15. Now, what you want to keep in mind here is that it's not like we're going to set this equal to 0. That actually would be kind of strange if I'm going to set it equal to 0. The truth is it's already equal. They're equal to each other. But when solving this kind of equation, that's right, we're solving a polynomial. So when you solve a polynomial from your algebra learning, you're going to actually make the equation equal 0. So we subtract 9 from both sides, and we get ourselves a quadratic. That's right, this is a quadratic equation, and there's different ways to solve those. Perhaps you can factor it. It turns out that this is not factorable if you study the numbers enough. So yeah, we can go to the quadratic formula. I'm not going to rewrite the whole quadratic formula, but it is the opposite of b plus or minus the square root of b squared minus 4ac, which comes out to be 72, and it's all over 2a, which would be 6. If you simplify this, you end up getting basically 2 plus or minus root 2. We'd have to do some simplifying, but I'm more concerned that you realize that 2 plus or minus root 2 is actually two numbers. Even though we don't do this often in math, we're going to write them as decimals because we can end up with either 0.586 x's or 3.414 x's if we simplify 2 plus or minus root 2. Now, what does this mean? Are both of these the maximum? Doubtful, unless it's a tie, unless we end up with the same value. The same value for what? Well, the same value for your profit equation. Remember, profit is revenue minus cost. So basically, I have to do what we've done for a lot of these problems, actually plug in. So I'm going to plug in 586, and of course I would plug that into the revenue equation and the cost equation and then subtract. I'm not going to show all that, and I'm going to tell you that you're getting 4,203. Now again, that's a profit, so I doubt that's just $4. Maybe it's $4,000. If everything's in thousands. But the idea here is to actually check both of these, and so we'll plug in 3414. Again, we're plugging that into the revenue minus cost equation, and that one comes out to be 9657. Well, you tell me which one is the maximum. It's going to end up a maximum profit of the 9657 when we produce 3414 of whatever it is we're making here. Well, what else were we trying to do in this problem? Oh yeah, we were trying to get a minimal cost. Now remember, a minimal cost is, according to our little fact here, it's when the average cost is equal to the marginal cost. So to find the average, I'm going to take my cost equation, which it's the original equation, the x cubed minus 6x squared plus 15x. And we're going to divide that by x. That's always how you find an average. You basically take the total and you divide it by how many. And then according to our little fact, we're going to set that equal to the marginal. So, of course, that's the derivative, which we already found in the previous problem. Ooh, boy, what do we get to do in this, this equation? Well, we're going to solve it, but relax, because first of all, when you divide everything by x, you end up with a less exponent, right? And it turns out that when you think about it a little bit here, once again, you basically have a quadratic equation. A quadratic equation that contains x squared, but most of these things, all these items, I want to move them over to the other side, add, subtract, do what you got to do. And this thing's going to equal 0 again. So we end up with 2x squared minus 6x, and that's it. So I don't need the quadratic formula to solve this. Perhaps just some simpler factoring is all that's needed. And so it's a little easier to solve this and see that x would equal 0, x would equal 3. Now, again, what does this mean? Well, apparently it means that if you produce 0 x's, oh, wait a minute, if you produce 0 x's, you're going to have 0 costs. Your cost is going to equal 0 because you didn't make anything. But if you produce 3 x's, well, your cost, now I'm plugging this back into my cost equation, that's the x cubed. Let me show that. I just want to make sure that we're tracking here minus 6x squared plus the 15x. So we can plug that back into the full cost equation, and that comes out, actually, to pretty round numbers, comes out to 18. So, I'm not an economic expert, but just as a little recall, hold on, this was my minimal costs. Maybe we could write actually a little statement here, minimal costs of 18 when x equals 3. And then what was it again? It was a max profit of 9,657 when x was 3, 3,414. Well, as we kind of thought in the beginning, these are not the same ideas. The minimal cost is just what it's going to take for you to spend the least amount of money. So if for some reason you don't have a lot of money, you could spend the least amount of money if you just make 3 x's or 3,000, if it's in thousands. But if I want to make the most money, then I'm going to have to produce, 3.4. I'm going to have to produce a few more. My point here is that this is interesting. This would be stuff that you could study in a business calculus class as you study economics and find out maybe how these two numbers, of course, are different, but yet seem to be both helping us to optimize the economic situation for this problem. So what's your assignment going to be? Well, it's a little alternative. It's not going to be out of the textbook. Instead, it's going to be what I call partner problems. You're going to be matched up with somebody, maybe a small group of 3, but basically each group is going to solve 2 problems. One problem that is similar to one that we did in the notes, and then one problem that's different, but not too different that you can't figure it out on your own. So we basically get you to do 2 problems as your assignment. Those will be distributed in the classroom, and that way you can show what you know, what you're going to know about optimization.